Okay, let's get started here. So today we'll talk a little bit about test number one. We'll also talk about the project, or project number one, and also continue in the graphics section. Are there any questions before we begin? Okay, so test number one, you've already seen the grade distribution here. Overall, it's a good distribution that we have. Now I understand that some of you may not be necessarily as satisfied about your grade as other students are. But just remember though, this is worth only 5% of your overall grade. And so there is obviously still time to make changes as necessary, as needed. Now, when you view your test that I emailed back to you, again, the way that I grade is I use the track changes tool of Word. And sometimes there can be misunderstandings for students about how best to actually review my comments. So here's just a question from some other graded item from another class from a couple years ago that I had. And so I just copy and pasted one question that was from this graded item. And you see here off to the left, of course, you see some red lines here indicating that there were some track changes. The problem, though, is you can't really see what those track changes are. This is usually the default of how Word actually has people view track changes. What some people don't know is if I go up here to review and change simple markup to all markup, now you can see exactly where my track changes are. And so I strongly recommend that when you view my my track changes on your tests and upcoming projects, view it this way rather than the default, which is what's called the simple markup. You'll be able to see my comments much easier. Okay, so I want to talk about just a few of the problems or few of the parts of the exam where I had, let's say, more than one student miss some points. So I just want to clarify some stuff here if it's still needed. You know, I give you the answer key corresponding to the test because I feel that that's the ultimate amount of feedback that I could give you, because you can see exactly what the correct answer was for each of the problems. Also allows you to see how, perhaps even if you got a problem right, how you can maybe answer the problem more concisely or taking a different approach. Okay, so for 2A of the test, so we have this multivariate normal distribution, and simply what you needed to do was draw the 0.01 contour on this for this distribution. And so in this particular case, pretty much everyone was able to realize, okay, well, I can go back to another program, copy and paste some code, use that as a template, then to set up my own program here to do this 0.01 contour. The problem that multiple students face, I think at least 3 in class, came across this when we were doing the test. I was getting a little bit of help. Was you got to be careful. While yes, you need to understand. You can use my code as a template. You still need to understand what's inside that template. And so the number one problem that I was seeing was that you needed to change what the x1 values were and what the x2 values were, corresponding to the actual probability distribution that you're using here, rather than what was in my previous program. So what was often happening is that students were maybe only evaluating for some values of x1 and x2, and maybe only getting this portion of the plot, and they were not seeing the entire contour. So just be careful about that. The next issue on the test was to state the next part on the test was to state the correlation matrix. And a number of students had some difficulty about I guess, what the question was asking. And so I'm here asking you, tell me what was not clear on this problem, so I don't, so I can improve in the future. Because when I see this, I say state the correlation matrix, and this I thought would be the easiest problem on the test, because all you need to do was go up to the covariance matrix, do one little calculation to find the correlation between x1 and x2, and essentially then you got the correlation matrix. Was there any misunderstandings with this particular problem? I know there were some students who were asking questions about it in class. I don't remember who. Although I do see a smile there. Was there anything that was misunderstood, or should we just move on? We'll just move on. And lastly, 3F. So how can one appropriately examine whether a random vector x truly has a multivariate normal distribution? And some people say, okay, well, you can do a scatter plot between x1 and x2. Well, okay, but what happens if you have an x3? What happens if you have an x4? What happens if you have x5? So notice here I'm saying multivariate normal. I'm not necessarily saying, constraining you to just 2 variables or 3 variables. And so because of that, you needed to go a little bit further. You need to say, well, all pairwise scatter plots between the corresponding variables. Now, the problem with that approach is it only evaluating normality 2 variables at a time. It's not evaluating variables, let's say 3, 4, 5 variables at a time. So that's the one issue then with this technique, for what I was looking for to describe any possible problems with your approach. Okay, so that's all I had to say about the test. Were there any questions? Okay, let's move on. Let's talk about project number 1 then. This is due Friday, October 6th at 5 p.m. It's over the graphics section of the notes that we're doing right now, and also then the next section of the notes, which is over principal component analysis. Working groups of up to 3 people. At least 2 people need to be in your group. Most of you have already completed this, but if you haven't yet, the week number 5 quiz. That's our group member sign-up quiz. Just indicate who your group members are. All group members need to actually complete the quiz to get credit. Okay, so let's take a look at the project. Okay. Excuse me? Yeah, it's been uploaded. I think I posted something to the discussion board about it Thursday or Friday? Yeah. Okay. Okay, so, in any kind of graded activity in a course, basically what you're trying to do is to show your instructor that you understand the material. And so that obviously is the purpose of this particular project. Especially since this is grad school, I like giving them some freedom about how you actually show me that you understand the material. And so on this particular project, what you need to do is find a particular data set and essentially show me with that data set that you understand, well, how to do a scatter plot, how to do some other kind of plot, how to do something else corresponding to the material that's in the notes. Now, so you can choose the data set. However, I need to approve the data set before you really get going on it. And so what I recommend that you do is before, and what we're going to need to do is email me the data set. But before you email it to me, maybe do some initial stuff with the data just to have a general idea that, yeah, I think it will work. Okay? And so in order for me to approve the data set, email me a draft of this initial work section of this outline of this project here. Now, whenever you complete a part of this project, I need to see all your R program output with code inside of it. So, similar to what's in my notes in terms of how I present R code and output, that's how I want you to present it here. And I do need all your R code and output, because when I grade this, very often I will actually just copy and paste your code and see if I get exactly the same results as you do. I won't do that for every single part. But typically, whenever I'm like, okay, I don't understand how this worked out, I'm going to probably copy and paste your code and try to run it myself. And if it doesn't work for me, well, then that's unfortunately a place where you can lose points. Now, there will be times too where you need additional information. So maybe you might need to interpret the results. Well, then you just simply type it in the project. So what I recommend that you do, and you'll see an example coming up shortly, is just use my Word file here as a template, and then whenever you need to answer a particular problem, just give you some space and then type it. Okay, so let's take a look at this initial work section. So tell me your data source. Maybe it's your own research, maybe it's a book, maybe it's something that you found on a website. Fully cite it, because I might want to go check it out myself. So especially if it has an internet location, give me that internet location so I can go check it out. Then, use R to read in the data set. Okay, display the first 6 observations. So let's say, for example, I wanted to answer this particular part. How would I do it? I put some extra stuff here at the end of the project. This isn't in the actual project that you can download. So let's say I was using the serial data. So similar to what we've done before, I would read in the data using the read.csv file. I use the head function, look at the first 6 observations. I run this all in R. I copy and paste the code and output into my Word document. And then I might have to go back and format it to make it look nice. So for example, let me just redo this. So I read in the data. Do that. I'm going to copy and paste it into my Word document. And here we go. This doesn't look very nice. Notice how things are not quite lined up as what we would expect. So this is where you would need to go back and format it so that everything does look nice. To help you out in formatting, what I've done is in my file here is I've included a word style called R10. So if I highlight this set of text, go up to R10 in my style guide, look what happens. It nicely formats it. Now you still might have to do a few small things, but I want your code and output to look like it does in my corresponding notes. So for example here, I just don't need that indent, so move that out. Now if there was some additional explanation that I needed for a particular part, well then I just simply type it. So that's the style. So number 3 here, provide a thorough description of each of your variables. Now just realize that if you especially are using stuff from your research, I'm not going to be expert in your research area. You are going to need to explain stuff. Don't assume that I'm a biologist, I'm an engineer, I'm an animal scientist. Don't make that assumption. What is your research question of interest? Well, think of this in terms of this project, in terms of what we're doing here. Well, we have multiple variables. We want to try to look for trends. We want to try to make sense of them. We want to maybe look for outliers, stuff that we've been doing in the graphics section. So phrase some kind of research question in that format. And then lastly, something basically from Study 1, define your population of interest. Specifically state why your sample is representative of that population. Okay. So, where can you get your data? And I've kind of talked about this before. Is that, ideally you might have something with your research. But if you don't, that's completely fine. Probably one of the first places that I would look, maybe I'm more old school here, is I would go to another multivariate analysis textbook and find a data set there. One reason is because if it's in that textbook, there's probably some analyses that they've done with it, and you might be able to learn from that. Then when you're using it for this project, or hopefully, as long as everything goes well with this project, we will continue using this data for future projects. There's a nice website from this guy who's a professor at the University of Florida. In their Department of Statistics, he has tons and tons of data sets there. And you can find some data there if you want to. You can go out and collect your own. So for example, you can go collect your own cereal data. It doesn't have to be exactly the same kind of cereal data that I have. I have sugar, fat, and sodium. Well, there's a lot of other variables that you can collect as well with the cereal data. Obviously, the data that you choose cannot be one that I'm actually using for our course. That would take a lot of the fun out of it for you and I. And the data cannot be obtained through something called complex survey sampling. If you don't know, you probably don't know what that is. Basically, what that means is that the units that appear in your sample had an unequal probability of appearing in your sample. So for example, let's say if I have 100 items and I want to take a sample size of 10. Maybe one of the items has a probability of 10% of being in my sample, while another item might have a probability of 1%. Unequal probability. That then corresponds to something that's called complex survey sampling. You no longer have independence between your sampling units. That's the problem. We're assuming that we do have independence. There's a whole course on complex survey sampling. It's called Study 4. I think it's just simply called survey sampling, where they would talk more about that if you're interested. And lastly, since this is a multivariate class, the data needs to have at least 4 variables in it. Now, that doesn't mean let's say that you're going to use some. Let's say you come across a data set, maybe from a book, that has 6 variables. And you'd say, oh, okay, Chris says that we need to use at least 4. So I'm going to drop 2 of the variables and just use 4. No, don't do that. Use all 6. Now, let's say also maybe you have a situation for your own research where you have 100 variables. Okay, that I understand. That's a lot. Perhaps narrow down let's say your questions of interest to something where you can work with, let's say, maybe 10 or less or something like that. So what I'm just saying here is don't go overboard by saying, hey, the more variables, the better. Don't do that. But don't go with the minimum of 4, if possible. And lastly, about choosing your data. I have to admit I'm not a big fan of genetics, in terms of genetics data sets. I have a hard time with some of the terminology in that field, and I've just never quite been able to get over that. So if possible, please do not choose a genetics example or genetics data set. If you really, really want to use one, then you're going to have to really, really explain the stuff. Don't make assumptions that I know genetics. Okay? So, what I recommend is that, let's say within the next week, don't waste time, definitely within the next week, do an initial draft of 1 through 5 here. Send it to me with your data. Then I will approve it, or maybe I'll have more questions for you about it. And then once you get my approval, then continue with the rest of the project. We got enough time here. I think I said that the project was due October 6th, so you do have some time. Just don't wait till October 5th to get my approval of the data. Okay, let's continue looking at this project then. Yeah.
And each group member should have their own data set, yeah?
Each group should have their own data.
Each group?
Each group.
So.
That's why you're working in groups.
Okay, so if we don't know, I mean, okay. If we don't know about the other, I mean, okay.
Yeah, so obviously, if you're in a group with someone who's in a totally different field, well, you're going to have to pick a data set or choose a data set that's not in either of your fields. So when you do turn this in, just email it to me, and I'll give you a confirmation that I've received it. So, if it's, let's say 8 p.m., well, let's say 10 p.m. the day that it's due, and you still haven't heard back from me, maybe I didn't receive it. So you should follow up. Just turn in one document per group. If you want to talk to members of other groups about the project, that's completely fine with me. Obviously, they're going to be using, well, every group needs to use a different data set. But still, one of the reasons of having group work is so that you can learn not just from talking to me, but also talking to your fellow classmates. And I encourage you to collaborate with others in the class so that you can learn the material. Any other questions before we continue here?
How many observations?
Yeah, obviously I don't have a set guideline there. If you have 5 variables and only 5 observations, then you're going to have problems. Let's say choose enough observations to make it interesting, but also don't choose too many observations where it just becomes a mess. Don't have it like a million observations. Think back, in the back of your mind when you do this project, you should be thinking, okay, I need to demonstrate to Chris that I understand the material. That should be your number one concern. And so you might have to, especially if it's data for your own research, you might have to deviate some from what you're actually interested for your own research. That's fine. You need to demonstrate to me that you understand these items. Okay? So, in the graphics part here, obviously, again, there's going to be some R code. You're going to be reproducing the output. You're going to be producing a plot. I need to see both the plot and the R code associated with it. With each of these plots that you're going to do, it's not just doing the plot, it's actually interpreting the plot relative to why we are doing these kinds of plots. Again, looking for like trends, looking for unusual observations and stuff like that. Interpret each plot. Sometimes you may need to do more than one plot to get at what you're interested in. That's fine. Just don't do, let's say, 10 plot. I don't need to see 10 3D scatter plots. Maybe do one, and if you feel as though that you're still not getting at what you need to, then you can do another one. So, first, do a scatter plot matrix. Well, that was the very first thing in the graphics section. Then, number 2 here, scatter plot. So you're going to need to pick 2 variables, but allow the plotting points to change in an appropriate way to reflect other variables. So like what we did with the shelf number. When we were looking at, let's say, the relationship between sugar and fat for the cereal data. Number 3, a bubble plot with appropriately scaled bubbles. And then the rest, 4 through 7, is stuff that we're actually going to talk about today in terms of these plots. 8, combine your results from 1 through 7 to see if you can come up with some overall conclusions. Then for the next set of notes, we have this principal component analysis section. Obviously, we haven't done it yet, so I'm not going to go over it right now. when we get to those that material, then I'll talk about it a little bit more. Okay, so I think I have covered everything in this project, enough for you to get started and get that data set. Okay? Any last questions before we move on? Okay. Let's see. So we're going to go back to this graphic section. And simply, again, we're looking to see how many, looking to see, we're trying to get as many variables as possible on the plot so that, again, we can look for trends, we can look for unusual observations. The next thing that we're going to look at real briefly here is a 3D scatter plot. You know, we've done three-dimensional surfaces before with the RGL package, and guess what? Well, you could do a scatter plot with this package as well using the function called plot3D. And it's fairly simple to use. So I already have my data read into R. So plot3D, I have an X argument, Y argument, Z argument, all correspond to what's on the X, Y, and Z axis. So notice I'm going to put sugar, fat, and sodium on this plot. I have some other stuff that you can guess what it is in terms of, like, for example, COL, color equal red for the plotting point. The size of the plotting point, the default happens to be 3. I don't know the exact scale that they're using. I chose to make it twice the default, so I put a 6 there instead. And then I'm going to put some nice grid lines on the plot, and the way to do that is with the Grid 3D package. You can see where I want the grid lines corresponding to what axes, the color of the grid lines as well. And so if I run that code, this is the plot that I get. I can rotate this plot just like what we would have seen previously with the RGL package, and we can see we have a 3D scattering of points. And so again, what we're doing is trying to look for trends here. You know, is there maybe some kind of like a 3D-ish linear kind of trend here? You know, it's really tough to see. I don't really see any specific trends. But you know, as I rotate my plot here, we can see that we are starting to have some points that are kind of separated from the rest here. So we have some potentially unusual observations being shown there. So we see these two right there. Let me keep on rotating. You know, maybe these points, let's see here. Sorry. There we go. Notice how these kind of points are separated from the rest as well. And so that would make me want to follow up on that. So let's focus on these 2 points here. And so, you know, it's nice to say, okay, yeah, I found some potential outliers. And so you can put that on your project. But, you know, if you're doing this in the real world, of course, you want to know, well, what observations are these exactly? You know, what cereals are these? So if we look at them here, we can see that they have low fat, they have a low sodium, and they have a low sugar content. Okay? So how can I have R tell me where those, or what those exact observations are? This is not in the notes. Just when I was going over when I was preparing for class yesterday, I thought, you know, it would be good to add this. It's not in the notes, but it's in my R program. I still need to upload this program to the, or with this change here, I still need to upload this program. So take note of that. So we saw that we had some very low sodium values. So what I could do is say, okay, R, let's look at all the sodium values. Which ones are less than 0.01? And so what I get is a bunch of truths and falses. And then to pull out of my data set those observations that correspond to a true. So notice here, this true corresponds to observation essentially 26. This true corresponds to observation 30. So to pull it out of the data set, what I can do is say, for my row numbers on my serial data frame, I'm going to put a bunch of trues and falses there. The trues will be returned to me. And here are the observations. So both of these are shredded wheats. And generally speaking, well, if you like cereal, you know this. You know, Shredded wheats are often thought of as some of the kind of healthier kinds of cereals. Kind of tasteless too, but that unfortunately happens with healthier things. I like shredded wheat though. And we can see that indeed, look at, there's no sodium, very low sugar, very low fat. And actually, I wanted my data set to be the one that has the adjusted values in it. Okay, where are we again? There we go. Yeah, that's a little bit better. Okay, so I have found those. And again, and then this is a standard way that people in R use to try to pick particular rows out of a data frame. It's through this technique where you have trues and falses as part of your row number area. Now, if you were concerned that maybe if I didn't say sodium less than 0.1, maybe I wanted to pick these up. Maybe you also want to do it for a second variable as well. Let's say, let's see, which ones did I use there? Let's say very low sugar too. So I want low sodium, low sugar. What would I do? Well, exactly what I had before. And then I use an ampersand to mean and. So I want sodium's less than 0.01, sugar's less than 0.05, and as you would expect, I get exactly the same thing. So on your own outside of class, what you should do is see if you can pick out these particular 3 observations here that seem to be kind of separated from the rest as well. Notice that they have high fat content corresponding to the other observations. They have high fat content and, let's see here, they have reasonable sugar content, they have reasonable sodium content. So it's just the fat for some reason. Those are the ones that are large. I think we've seen these actual observations before. I think these corresponded to the ones, one was the Oreos, and one also had, or 2 other ones had lots of nuts. And nuts have, a healthy fat in them. Well, let's see here. Now, one thing that can be helpful is whenever you look at these 3D plots, sometimes it can be kind of hard at times to see where points are in this 2-dimensional representation of a 3D area. And so what can be helpful, though, is that you can draw what are called needles up from the bottom of the plot to help you better see where those observations are. And the only thing that you need to change corresponding to our code is to add a type equal h. Height, you can think of h for height. And so if I do that plot, we can see where everything is a little bit better. Now do note that actually I did the plot twice. The first time I did the plot, I only got the needles. Then I did the plot again, where I had a color of red for the plotting point, and I said add equal true, meaning add it to the previous plot. Now you might also want to do this exact same plot relative to the shelf as well. You can take a look at how I actually did it here. Notice I actually did 4 separate calls to plot 3D to get the 4 different colors. Okay, so let's move on. So you can get 3 variables easily on those plots. You can change the plotting point color to get a 4th variable. And we've seen pretty much you could do up to about 5 or 6 variables on plots that we've seen before. But what if you have more variables? How can you get those variables displayed on the plot? That's what the remaining parts of the notes talk about. These are now going to be plots I would expect that probably most of you have not seen before in any way. Now, the first plot is called Chernoff faces. You're not responsible for this. I almost actually deleted it out of my notes. I decided to leave it in So I can talk about it hopefully just for 1 minute, because sometimes you'll still see people use these plots. They're inferior to the next set of plots that we're going to do. The key thing is, here's a Chernoff faces plot of the corresponding serial data, and basically facial characteristics correspond to each variable. So for example, you can think of a wide head as maybe corresponding to having high sugar content. A small head corresponds to low sugar content. Instead, what we're going to focus on is a star plot, or star plots. Let me actually show you a star plot of our data, and I think this will be helpful to understand what this represents. Let me get this better displayed. There we go. So we have 40 observations, and so that we can see, you can see that we have a shape. We have essentially a shape for each observation. So each of these shapes, which are called stars, has a display for it. And imagine that, let's say for the sugar variable, we find whatever the minimum value is. I think it was 0. We also find what the maximum value of all the sugar content is. And I'm going to say it would go out this far. And so for, observations that fall then anywhere between 0 and that max, then we'll have what's called a ray extending out from the center. Then for sodium, which is measured in a different scale, the minimum value will be right here, the maximum value will be right there, and then corresponding to the other, for the actual variable values, for the 40 observations in the data set, I'm going to fall somewhere in between relative to where that minimum, relative to where that maximum is. I'm going to do the same thing for the fat. So again, what we do is we draw rays out from the center of each of these graphical diagrams, corresponding to how large a particular observation's value is for that particular variable. So for example, let's look at number 2 here, observation number 2. So it has, looks like no fat. It has only a little bit of sugar, but it has a high amount of sodium. So let's go back to the actual data set itself and see if that is the case. So this is observation 2, so the numbers there correspond to actual observation numbers. Post-toasties cornflakes. Notice, let's actually do a summary of cereal. Notice that sugar value is 0.07, and we can see the maximum value is 0.05. About. So essentially, this ray should go out about 14% of that maximum that the ray could go out. And indeed, we can kind of see that indeed that's what's happening there. But in terms of the sodium content then, it has 9.64. The maximum is 10.7. So we would really expect that ray to go out pretty far. You know, about 90% of that total distance that we see in this legend area. And indeed, that's what happens. We can see that serial number 3 is very similar. Well, what one was that? That was Kellogg's cornflakes. Oh, another cornflakes. That makes sense. Just a different brand of cornflakes, but it has similar sodium, sugar, and fat content. Okay. So this is a nice graphical diagram for my entire data set. So what are some unusual, this kind of plot is very helpful for finding unusual observations. What do you think some unusual observations are? Give me observation numbers. I'm sorry, say it again. 13?
No, 30.
30, okay, I'm sorry. 26 and 30. Yeah, immediately those stick out. Remember, we just saw 26 and 30 relative to that 3D scatter plot. Let me come back to that. It was these two right here. So notice how this plot allows you to see this as well. Let's see here. Let me make this a little bit smaller. What were some of the other comments that I had? No, we'll get to some. Well, I was actually getting ahead of myself, but definitely 26 and 30 stand out. Let's talk about how we can do this plot. So simply, there's a function called stars. It's in the graphics package. The x argument corresponds to my data. Remember, I only want columns 8 through 10 of my serial data frame. I can specify the number of rows, the number of columns of stars. Draw.segments equal false. You'll see what happens if I do true to allow you to understand what this means. In key.loc means key location. In other words, where do I want this? Now I said 3, 12. 3 corresponds to the x-axis, 12 corresponds to the y-axis. Obviously, we don't have an actual normal x and y-axis being displayed here. But you can imagine, sometimes it's best just to do trial and error to actually find what this is. But, and sorry, now I don't remember. I should check this before class. I believe that this is 0 and 0, and so that this would be essentially 12 according to its scale. Again, since we're not necessarily plotting, like we have like 6 centimeters or 5 centimeters or something like that. We don't have that, so it's hard to understand what R is using for its actual scale itself. And so what I recommend often with these kinds of plots is just do some trial and error and find an empty spot on your plot to put this key. But this is very important to have that key there. Now, a different version of this plot is when you do draw.segments equal true. And this is what we get. And actually, I prefer this version because of the coloring. And I think you can see stuff a little bit better this way. So you might be thinking, oh, this is a pie chart where each corresponding section of the pie, its size, relative to what we normally think of as a pie chart, corresponds to how big a particular variable is. That's not the case. So instead of, let's say, having a ray coming out from the middle, instead all we have is this segment of my plot. Well, that wasn't good because now it's kind of hard to see. We just have this, let's say, pie chunk being extracted from the middle of the plot. So for example here, when we had that very high sodium content for number 2, look how that is actually represented. That green is coming very far out. The black is not coming out much at all, and we don't see any red. Notice we have 26 and 30, similar to what we saw before. Okay, so just to make sure we understand this kind of a plot, so which cereals here appear to be high in fat content? Give me numbers. I'm sorry, say it again. 8? 14, 20? Okay, so let's see what I put here. Yeah. Notice these are the ones that have peanut butter in them. Peanut butter has, of course, a nut, so it's going to have high content. Notice we have pecans for number 25, and then we have those really bad Oreos. Oreos O's for number 20. Well, how about high sugar content cereals? And just focus on the black there. 7, 12, 16. Yeah. So These are definitely marketed to kids, these particular cereals. High sodium content, let's see here. Probably, well, we've already seen like kind of a 3, maybe a 10, maybe a 23, and yeah. So the key is, you can really see outliers by these kinds of plots. It's a little bit harder to see trends, but you can imagine, let's say, suppose some of these plotting points, a significant number of them have, let's say, very large green and very large black. Well, you could see that. If, let's say, instead, too, you had a plot like this where you only had very large green, or you only have very large black, or you only have very large red. Well, that's a trend. What that's telling you is that probably these companies, they choose, okay, I'm going to have a high sugar content, and maybe I'm using sugar to replace the fat and sodium to make it taste good. Or I'm going to have a high sodium and not have much sugar and fat. Where the high sodium hopefully will help it taste good to get more sales. Okay. Now, something that might be helpful then on your own project is that there is a labels argument for the stars function that you can use to actually put word labels corresponding to the observations. Like you can imagine each of the cereals actually having the name of the cereal there. I chose not to because those names were kind of large. Now, I would say the number one problem with doing star plots is that let's say if you have a larger data set. Let's say that place-kicking data set that we saw before, there were 1,425 observations. That would mean I would need to have 1,425 stars. It's going to be hard to make sense of all that. So, especially then, on your project, if you have a larger data set than like what I had here for that size of 40, you might want to think, okay, how can I show Chris that I understand what a stars plot is and still make it make sense relative to my data problem? One way is to somehow summarize your data over particular variables. So let's say, for example, with the place-kicking data set, I actually knew the names of the place kickers. So I have 1,425 place kicks that were done from about 40 place kickers. I know that. In my data set, version of the data set that I gave you, I don't have the place kicker name with it. But what I could do is, let's say, find the mean for variable 1 for each place kicker. Find the mean for variable 2 for each place kicker. And then now display a stars plot for each place kicker, displaying their mean. So that's how you can adjust, doing one of these plots to satisfy your own needs for a particular data set. Here's another plot that and again, the stars plot, you can see how you could have a large number of variables. Another plot where you can have a large number of variables is what's called a parallel coordinates plot. This is probably my favorite plot out there. I'm a statistician, so I guess I can have favorite plots. And the function that we're going to use is called parcoord. It comes from the MAPS package. This stands for Modern Applied Statistical with another S. There are other functions that are out there. And I thought about using one of these other functions when I was revising my notes over the summer. And in the end, I decided to go back to using this one. I thought that would be the best for our course, but you're welcome to explore some of these other functions as well. Now, this is another example of a time where I think it's just easier for us to take a look at the plot, and then I can explain what everything is representing. So I'm going to make this a little bigger. So this is with the serial data. Okay. So let's focus on sugar here. Okay. Suppose you go through your data set and you find the minimum value for sugar. Find that particular observation, and then you plot it on this axis at the very bottom. Then you look throughout your entire data set, and you find the maximum sugar content, and you say, okay, I'm going to make that the top of this axis. Then, for all the observations that fall between the minimum and maximum, I'm going to plot them relative to their actual location. So, for example, if I had, I think the minimum was 0, the maximum was like 0.56. So let's say if I have a cereal that has a sugar content of 0.28, well, I would put that right there. I would plot that. If I had one that was, let's say, 0.05, well, that would go here. So in other words, I'm kind of rescaling my observations so that I have the minimum at the bottom, maximum at the top. Well, how would you do this in a more coordinated manner, let's say? For each observation, you take their value, subtract off the minimum, and then divide by the maximum minus the minimum. And if you can imagine a numerical scale then, even though we don't see one here, imagine a numerical scale for that sugar axis. That's how you would plot all the observations. Now for the fat, you do exactly the same thing. You find where the minimum is, you find where the maximum is, and you plot everything relative to that. So for example, you plot right there. Now, the strength of this plot then is the following. You connect, for the same observation, you connect their corresponding sugar and the fat values. So for example, the minimum sugar value, that same exact cereal has a fat value right there, and they're connected with a line. And you do that throughout, for all the sugar and the fat, for every single observation. Do it for sodium, and notice also I have an ID variable there, which just corresponds to, is it observation 1, 2, 3, up to 40. Okay. Oops. Do some erasing. Okay. So these kinds of plots can be helpful to see trends. Well, it allows you to see outliers like what we saw at the start spot, but this allows you to see trends a lot more. Notice, and now I'll explain how to do this plot in R shortly. Notice how I've color coordinated each of the observations, each of the lines then, corresponding to shelf number. So, relative to some of my original research hypotheses, let's say, do you see a particular trend here? Shelf 2 has high sugar. Yeah, we've seen this in other ways before, but notice how all these red lines are up there. But then you might be wondering, okay, if it has high sugar, do I see something similar? Do I have maybe lower fat for all of them, or higher sodium for all of them? Do we see that? No, we don't. Okay, so we've learned something about our data here. What are some potential outliers across the variables, all the variables, excluding ID? So an outlier, of course, would be you tend to have unusual values. Excuse me? You mean up here?
Yeah.
Yep. So we had some of those high fat content ones. Remember what we saw with that 3D scatter plot and what we've seen elsewhere. The 2 peanut butters and the Oreo O's. Those are actually those observations. Look at these here. Low sodium. Let's follow the line. Relatively low fat, not the lowest, but the lowest sugar. Also, low sodium, not the lowest fat, but kind of low. Low sugar. That corresponds to number 26 and number 30 as well. I'll talk about how I know that coming up. But you might be also wondering, okay, were there really, similar to what we see for shelf number 2 for the sugar, are there maybe other shelves that tend to have, let's say, really high fat content or really low fat content? Do we see any trends there? I don't think so. It's just that shelf 2 where we're seeing it. If you remember before also, we thought, well, maybe shelf 1 also tends to have high sugar content. I mean, obviously, again, for kids, it's easy for them to go to shelf 1 and pick stuff up. Well, let's take a look at, shelf 1, which would be denoted by the black. I mean, we do tend to have some higher sugar content ones, but we have a few low sugar content ones that seem to throw everything off. Okay, so let's talk about how we did this plot. Okay, so it's from the mass package, so I need to say library mass this function. And we've already done this before, but I just do this here for emphasis. I want to create an object called shelf.color that gives me my coloring for the particular shelves. So I just repeat black 10 times, red 10 times, and so on. And then the function to do this kind of a plot is called parcoord. X argument, where my data is. So column 1 is my ID variable. Often in these kinds of plots, it's very helpful to have an ID variable. Columns 8 through 10 was the sugar, fat, and sodium. The color for each line is in shelf.color. And then I can put a title on the plot. Let's see here. Let me actually do the plot in here. Okay. Then I want to put a legend on the plot. We've seen legends before. Everything here is review. So for example, legend, that argument for the legend function allows me to put the corresponding shelf numbers. But this is new right here, locator 1. We have not seen locator 1 before, is that correct? Okay. So let me just show you what happens when I do this. This works very similar to the identify function that we've seen before, where when I come over to my plot, notice how my plotting point now, or my mouse is now a plus sign. It's wanting me to add something to the plot. And so if I click here, left click, I drop in my legend. So what locator 1 allows you to do is to drop stuff into a plot one time, locator 1, and it allows me to specify where I want my legend. Now the reason why I do that rather than specify like what we've done before, an x coordinate and y coordinate, is notice we don't have an x-axis scale, we don't have a y-axis scale. Sodium is on a totally different scale than sugar. Just everything is rescaled to be between the minimal and the maximal. So that's why it's often easier just to do this. In fact, you can use, maybe I should have done this before, with that stars plot, I have used a number of times in the past, used this locator 1 option to just drop in my legend wherever I want it. Now let's say, well, let me come back here. So you can get kind of an idea of particular observation numbers by looking at this ID. But I have to admit it's going to be pretty tough to figure out that indeed that this is 26 and 30 because you're going to somehow follow the path here. And it can be kind of difficult, especially if you have a larger number of observations. It can be difficult as well. So what you might want to do is that you see, okay, we've seen how we can identify a particular observation from my data frame. So let's say I want to tell R, highlight observation, let's say number 26 on my particular plot. How can I do that? Okay, I did actually ended up doing this a little bit differently than I remember. Let's say if I want to highlight observation number 1 in my plot. here's one way to do it. Everything's exactly the same, except for I'm going to use a LWD for line width. And I want the width of that first observation to be 5. The remaining observations to be what ends up being the default, which is just 1. So I combine together 5 and 1. Okay, so you can see all my line widths. And then if I highlight this code and take a look at the plot, oops, don't want that. Now you can see that particular observation has been highlighted. You could do this with multiple observations as well. Now, there are, and this is when I was again revising my course notes over the summer, this is one area that I thought, okay, I really want to use a different, a different function for this, because there's one thing that this particular function doesn't give you that at least one other function in R does give you. And that is you can do what's called brushing. So with my mouse itself, with some of these other, well, with at least one other function, is let's say if I want to automatically highlight, let's say, observations 30 through 40, what I could do is take my mouse and just brush over, just click on it, this area where you see my mouse right now, and automatically throughout the rest of the plot, all those observations will be highlighted. And that's a really cool thing rather than us doing it manually. Here's a package that will do that for you, iPlots, and I give you some code that allows you to investigate that further if you want to. The reason why I have used this before in this class, but I decided not to this time, is that you do need to have Java on your computer for this to all work, and I guess I just prefer not to put Java on my computer if I don't have to. Okay, let me see where we're at. Let's see if I've talked about all these trends properly. Okay, so yeah, we've talked about that. So let me give you another example where I've actually used parallel coordinates plots in my own research. And I think it's helpful for you to have some background here too. So for, many of you will have, will be actually working with a statistics professor, even though you're not a stat major. You might have them on your committee. Or you might just need some help from maybe our consulting center that we have. And so for faculty in a department of statistics, you can have up to 3 different parts of your appointment. You can have a teaching part, which obviously you're teaching a course. You can have a research part, which means that you are doing research that forwards the statistical discipline itself. You can also have a consulting part of your appointment, which means you're engaging in research, but not necessarily in your own field. You are applying known statistical methods to solve a problem in biology or animal science or something like that. In those kinds of cases, you are not the first author of a paper. You are maybe, let's say, the 3rd or 4th author. You're providing support service. You might do something interesting with the statistical analysis. I'm not necessarily trying to degrade that. It's just that the primary purpose is to forward animal science or forward biology, and you're helping to use statistics to do that rather than forwarding the statistical discipline itself. Now, my appointment is teaching and research. I don't have consulting as part of it. And so this is from a paper, a statistical research paper that I wrote, where I use a version of a parallel coordinate plot. And the purpose in this is to give you an idea what statistical research is that I had 4 different methods to estimate some kind of model. You can think of it as a regression model. and I wanted to compare them. And so what I did was perform what was called a Monte Carlo simulation study to make this investigation. At least this is one aspect of my paper. And so what that means is I simulated some data, and I applied the 4 different methods to it, and I estimated what you can think of as a slope coefficient for a regression model, a beta hat. So you can think of it as beta hat 1. So I simulated some data similar to like what we did with the multivariate normal distribution earlier, estimated the model, tracked my beta hat. Then I simulated another data set. It did exactly the same thing. Now I did this a lot of times. I think it was 500 times. And then I did a plot of the results. So on the left plot there, we have a box plot, side-by-side box plot. You've all seen these before. On the x-axis, I have the different method that I was using for the estimation. My y-axis, I have what beta hat 1 is. And then you see a red line going across the plot. That's what the true value of beta 1 was. Since I simulated the data, I knew what it was. And so what we can see in this is that the individual method results in the smallest amount of variability. This was like the Stainer method I needed to compare it to. But we can see if I use the alike, I get a similar amount of variability, a little bit more, not much. But if I use random and if I use different, I get a lot more variability. Okay. Now, I purposely then did a parallel coordinates plot on exactly the same y-axis scale as what we saw with the box plot. So the thing that I did differently here than what we've seen for a parallel coordinates plot before is that since each of these 4 methods, you can think of these as 4 of our multivariate variables that we have, for each of these 4 methods, they're all measured on exactly the same scale. So how about we just put that on the y-axis? And so and you'll see this shortly, I had to go into my par-chord function, make a little bit of a change to it so I could do this plot exactly like this. And so what we see in this particular plot is that for one simulated data set, my beta hat was about negative 0.09. Then for exactly the same data, when I estimate it with the alike method, now I'm at about negative 0.12. And then if I estimated it with the random method, I'm at about negative 0.09 again. And if I estimate with a different method, maybe negative 0.08. So I can see what's happening across these different methods. Just like with the box plot, I can see that I have a different amount of variability with each method. But this also allows me to see how consistent my estimates are from one method to the next, because I have these lines that are connecting the actual values. So we can see how these lines, they do overlap some, they cross some, but they're not really too much. So what this is saying is that my alike will give me similar results for my beta hat 1 compared to my individual. But now as we go to random and we go to different, for example, look at this here. The largest random value ends up being the smallest different value. So from this research then, that makes me worried if I wanted to apply this different method, because I can get totally different results. And so this is an example of how, parallel coordinates plots can be used. This was very useful to me, that I don't have much consistency, because I see everything kind of moving all over the place. But I do have consistency here. And this was helpful then in my research. So, how did I do this plot then? So the reason why I'm going over this example is to help illustrate some of the benefits of R. If I wanted to actually see the actual function code for par-chord, all I need to do is go to a command prompt, type par-chord, and I can see my function. And depending upon your level of being comfortable with R, it might be a little bit more difficult to read this code to figure out what's going on. And so what I simply did was I said, okay, I'm going to set X to be my data. I'm going to set my color to be 1, and so on. And then I execute this code line by line, and I look at what does Rx give me? What does X give me? What does matplot give me? So I can figure out what each line of the code does. And from there, I figured out, okay, if I want to have exactly the same y-axis for each of the variables on my plot, all I need to do is delete this out, and I can do my plot again. And so I created a function called parcourd2 that had that stuff deleted out. I made some other small changes. And this is the actual function that I use to create my plot. So I tell you this is that so that you can understand how if a particular function R doesn't meet your needs, take a look at the code, and you might be able to figure it out and make a small change to it to satisfy what you need to have it done. Now, one last thing about parallel coordinates plots. So as I said, that is probably one of my favorite kinds of plots out there. Or it is my favorite. One needs to watch out for something, and that is for overlapping lines. Let's say on this plot, not just 40 serials, maybe I had 400 serials. I'm going to have some overlapping lines. And so what that means is that some lines could be underneath other lines. And you might be missing something then, some kind of trend. And so that is one particular problem that can occur with using parcourd in this kind of situation. So what do you think could be done to partially alleviate this problem?
Increase the dimension of the...
Well, yeah, I mean, you can make the plot even bigger, but eventually, still, you're going to, depending upon your sample size, you might run into that problem.
Divide the data into plots, like plot one in front of each other.
Make multiple plots?
Uh-huh.
Yeah, that's one thing that you could do, yes. But if you only wanted to have one plot, what could you do? How it change the ordering that everything's plotted. So instead of, let's say, plotting observation 1 first, how about observation 40 first? Think about, since we're running out of time here, think about how you could simply, let's say, reorder your data so that you could actually do something like that. Okay? Okay, so let's see here. So we're running out of time here, so let's talk about what's next in our class. Of course, I'll have my office hours after class. Don't forget to complete that week number 5 quiz. Thursday, we will continue with graphics, and I think we will actually get to the next set of notes, principal component analysis. Then looking further ahead. Generally speaking, there will not be more weekly quizzes. I did that because we didn't have projects yet. Now that we've done enough material, we can have projects. That will be the primary way for me to assess you and for you to feel as though, or for you to understand if you're comfortable with the corresponding material. At the end of the semester, there will be at least one small quiz, but it's going to be relatively easy. Project number 1 is due now Friday, October 6th at 5 p.m. And looking even farther ahead, test number 2 is Thursday, October 19th. It will be over graphics, this new thing called principal component analysis, factor analysis, which is the next section after that, and there might be one other thing on it as well. Okay? So that is all for today.